Hey, what's up? Welcome back. This is day 12 of the 2021 Advent of Code. We're solving these with Ruby. And this one is all about finding all of the paths through sort of a graph when you have a source node and a destination node. And then there's a couple of different little tricks mixed in. So this is the way that we receive the input is sort of the edges, or this like, okay, so in graph terminology, a vertice or a node represents sort of like a dot on a map or a dot on a graph. You can sort of think of that as like the like a city in a map. And then the edge is going to be the road between the cities. So that is kind of like the connection between two nodes. So here we have like start and A. We were receiving this as kind of like the two nodes and their relation. So here on like the drawing of the graph, this kind of like input here would help us build this connection between start and A. And it turns out that if we have like all of this same input, it would look like a graph like this. And our goal is to find the number of distinct paths that start at start and end at end. So you can go from like start to A to end, or start to B to end, or start to A to C. And then the one trick is that you can only visit the small caves or the caves that are lowercase one time, at most one time, and you can visit these big caves as many times as you want. And so the trick here, instead of just having like a standard path like finding algorithm where you can just like generate all the paths through the graph, we have to be able to kind of like go back and revisit certain nodes. So we'll go through the process of implementing this, and hopefully hopefully we learn some stuff. All right, so we're gonna go in here and add day 12, and in here I'm gonna add graph.rb. I don't know what we should call it, but that seems fine. Day 12 spec.rb and require relative day 12 graph.rb. I like looked up a bunch of snippets, realizing that I was typing like the same stuff all the time. For Vim and snippets, I use snipmate, which is a little bit on the older side, and I'm super excited to start using GitHub Copilot, and there's a video on the channel getting that all set up, but I didn't want to use it for these videos because it basically writes like the entire thing for you, and I do kind of feel like it's a little bit of cheating. All right, so the first thing we want to do is build a representation of the graph that will help us work our way through it. And so there's a couple different ways you can do that. There's several different approaches to building representations. And when I went through this, I actually took a couple different approaches. Like one was building each node as its own class, like in an object-oriented way. And then that node was related to other neighbors. But I think that, so I saw some solutions that just used an adjacency list. I think that might be better. So let's try to do it that way. So we're going to have some method that builds an adjacency list from the input. So this is going to be something like graph is equal to build graph. And our input will just kind of be the lines that we're getting from input. So this is kind of like, I guess we'll just, take these in as strings. And then we want to split on that. We're going to split on that sort of dash, and we should expect that we get back a graph that looks like this. It's going to be a hash, and there's a couple different ways you can set this up. So you can have it be like string to string or string to list of strings. For us, let's just keep it easy so that we know that we only have a unique set of neighbors. We'll use Ruby's set class. So we can say something like start points at. So in this case, start is related to some set of other nodes. So in our case, it's related to A. It is related to B. And then, I think that's a good start there. And then we have to put in A. So A is related to start, because it's going to be both ways. It's going to be like bidirectional because it has that property where you can go back through the uppercase letters. So A is also related to B, also related to C, and also related to end. So we've got an end in there at the bottom. Is that right? So start, oh, it's not related to itself. Okay, that's good. All right, so then we have B. B is related to start. B is related to A. B is related to D, and B is related to end. Then we have C, and C is just related to A. And then we have D, which I think is just related to B. Then we have end, which is related to A and B. I think that might be what we want. All right, so let's say build graph. This is going to be a method that takes in our input lines. Maybe we'll just call these like lines or something. I don't know, edges. Not sure. And then we'll say edges dot split on. Actually, yeah, I guess we have to map over it. Edges dot each do edge. And we'll say edge dot split on dash. I don't know if it's really technically the edge. People are probably going to call me on that, whatever. And then that's going to give us like point A and point B. And A and B are just like the two nodes, right? And so we want to build our adjacency list. And so here's a trick that can be really helpful when you're initializing a hash. You can initialize that hash so that when new keys are added to the hash, you can set like a default value. So if you pass a block to new, that accepts in the hash and the new key. So now we can say hash at key is equal to set.new. This is really helpful if you're building like a counter cache type thing, or if you want to collect up like arrays of arrays or hashes of arrays or things like that. Okay, so now we can say graph at A, and we want to add B into the set of neighbors for A, and then we want to do the same thing but the opposite. So B, we're going to shove in A. So then we'll return our graph at the end, and that should be our adjacency list. Cool. So we have a passing test. The next step here is we want to, we'll just build the thing that goes through and finds all of the paths through the list. And I think the easiest way to do that is to start with something super simple and say it finds paths through a basic graph or something. And we'll just start with we'll start with building a more basic graph than this. And we'll just have it be start points at A points at B, and B points at end. And then we'll expect that find paths through graph to equal something. So this is going to be all the paths. To start, let's just try to solve the simple case of just going from start to A to B to end. So we'll have start A, B, end. And the output that it wants is actually just the number of paths. So in this case, we just want to count up the paths, but it is helpful to just see what all of those unique paths are. And that it's it's helpful for debugging. So we'll start here, and so we've got to implement find paths through the graph. And in practice, we might take in a start and an end and whatever, but for now, we'll just say that we have some paths to visit, and this will start with our start node, and then that's what we're gonna ultimately, so then we're gonna, this will be the queuing mechanism that we're gonna use to track each of the neighbors that we want to visit. And so while paths to visit empty, while it's not empty, what we want to do is we want to pop off the path that was most recently added. So we'll have a current path is paths to visit dot pop. And then what we want to do is just check that path. And if that path ends with an end, then it's a valid path, and we want to include it for our results. In fact, let's keep track of those. So valid paths is some empty list, and that's what we'll ultimately return down here is valid paths. And valid paths are all the paths that have an end or that end with end. And so here, I guess we want to say something if current path.last is equal to end, then we kind of want to return that, or add it to valid paths current path.pop, or a current path Yeah, so let me think about this. If we found an end, we don't want to keep going. So let's just say next here. So we'll look at the next thing. So that's kind of, it's almost like a base case or whatever. Like we're not doing this recursively, but I would consider that sort of like the common case. Now the next case, if we didn't find the end, we want to iterate through the neighbors of the current, like of the last node that was added to the current path. So we want to say graph at current path.last each do neighbor. So that's going to give us like the, this will help us iterate through the neighbors in that adjacency list. So this is actually iterating like through the set, right? And each neighbor is going to be a string value. And what we want to do is we want to add to our list of paths to visit. Paths to visit is going to be the current path plus the neighbor. So this is gonna, we're kind of just like appending the neighbor to the current path. Yeah, so that will actually like, when we do this concatenation here, that's gonna create new paths. So like every time we visit a neighbor, it's gonna create a new path and sort of like fork off. And then, yeah, okay. So then the other thing is that we only want to add, or we only want to fork if we've never actually visited this neighbor. So we could, I think, yeah, we could keep track of like visited, but I think we can also just sort of hack this by saying like, we already have the current path right here. We're looking at the current path. And what we're trying to avoid doing is adding duplicates of this neighbor into the current path. So we can say like if current path.includes neighbor, or if it doesn't include the neighbor, I mean, then we want to add it to the paths to visit. Let's see what this gives us. That seems too easy. All right, so now let's make it more complex, and let's make it so that we can go through yeah, so that we can go through A or B. So start points at B. And then we should get like a couple more interesting paths here. So start, B, end. And also we didn't really like talk about the case where you can go, you can repeat visiting the uppercase letters. So we should really have like another one in here that is like, well, actually instead of start B, let's add A to end, because that will make it so that we can go through start B end or start A B A end, I think, and also start A end. Yeah. So that should be our list, but we got, what did we get? We got 2 things, but we expected 3. Okay, so this is where we have to add the case where you can visit the big, the large neighbors, or like the bigger caves more than once. And so what we can do is, in order to allow supporting visiting that larger cave more than once, we just want to like skip this guard clause if the neighbor is uppercase. So we want to say something like, actually, is that a thing? Let's see. So pry a dot is upper. No. Check if letter is upper Ruby. I was gonna just say like upper equals. Oh yeah, okay. Is that the right thing? Oh, that's neat. Regular expression. Okay, well, whatever, that's too fancy. We don't need to be that fancy. We can just use this. We can just say like if neighbor is the same as neighbor.upcase. So if the neighbor is a capital letter or the neighbor is not in the current path, then add it to the current path. And that should help us get what we're looking for. Okay, so I think these might be the same thing. they're just ordered differently. And so instead of using equals, we want to say contain exactly. And we want to remove that. Run it again. Cool. So now we've got all of our tests are passing. And I think we can just write some driver code now. So going back to the graph here at the bottom, we can say, let's see. So we want to read in the file.readlines argv.first map chomp. And I guess that's kind of lines, or so that should be our edges. Build graph. And then we want to say find paths for graph. And we want to, let's print out .length. And let's add some example input here. And I think they give us, yeah, so here's some example input. There should be 19 paths through it. And let's see. Uninitialized constant set. Okay, so require set. 19. Okay, so that's working as expected. And then this one should have 226. So let's go look and make sure that we work for that one. 226. Fantastic. All right, and then my answer was 5228. I guess we got to add our input here, and it looks like this. Okay. So we'll run on our input 5228. Okay, cool. So we can pick one single small cave to visit twice. And so that is a new constraint for part 2. This is kind of like part 2. So I guess like this was where we were checking whether or not we can visit that path. So I think what we want to do is basically the same thing as this, but we want to be able to visit a small cave twice, one single small cave twice. And so let's add a helper method like duplicate or like duplicate small. And that's going to take in a path and tell us whether or not we visited small things twice. We'll select out those that are where one is the same as one dot down case. So that should give us all the small letters. And then we want to call, is there like a duplicates method? Or no, I guess, how do we want to do this? Tally. So tally is a really cool method. Let's take a look at how it works. So if you have some list, 1, 2, 1, 3, 4, whatever, 4, 5, something, something, and you say dot tally, that gives you a hash where like the value is the number of times that object appears in the list. So if we use tally and then say dot values, and then dot 1, 2. Okay, so I think so. This was another enumerable method that we saw when we were checking out the docs, and so I wanted to use it. So 1. So let's see if we can use that. Tally dot values dot 1, where there's like 1, 2. So duplicate smalls, and if they're yeah, so if we've already duplicated the number of smalls, then we don't want to add it. So I guess if there's no duplicate smalls for the current path, or yeah, okay, so let's see if that works. So let's run it on some example input, and we get oh, actually, let's run it on this original input. And I think that's what the like reference number is showing us. Okay, so if we run it on that input, slightly larger example above now has 103 paths through it. So, oh no, now the 36 possible paths. Okay, so we didn't get 36, we got 63. So duplicate small. The other thing is that you're not allowed, okay, there was another stipulation here. However, the caves named small and end can only be visited exactly once each. If the path already has end, then we don't want to add end again. So let's do it this way. Next, if current path includes end and neighbor is end, and the same thing with start. And let's see what that gets us. Okay, that gets us to 36. So that was the example answer. And then the slightly larger example above has 100 or 103. And the larger example now has, wait, slightly larger and the even larger. Oh, here's the slightly larger. Okay. And this one we were thinking has 103. Okay, that has 103. Great. I'm just going to run it on an input because I think we're pretty close. And ooh, wow, it's taken a long time. Okay. Okay. Come on, computer. 131,228. 131,228. Awesome. So this was generating all of the paths through a graph when you have a single start and a single end, a source and destination, sometimes they're called. So this was a fun one. There's a couple of things that I wanted to refactor though. So let's just play around. But if you're satisfied, you can bounce out. But what did I want to show? Oh, right. There's an interesting thing we can do here called tap. So we could say like hash.new.tap do graph, and tap basically just like creates a wrapper around this so that we don't actually have to define graph on its own. This can sometimes be like referred to as I don't know, like there's like the T command in Unix that you can like pipe input and output to that can be really helpful. So tap is a cool feature. Let's make sure that our day 12 specs still run. And actually, you know what? Now that we have support for multiple, now that we have support for multiple directions, that one isn't going to run anymore. But this one still runs, so that's cool. So tap is something that you might want to look into. It's kind of like an interesting tool for tapping into parts of a process. One of the reasons why people don't like to use it is that it ends up increasing like the indented, like how indented all your stuff is. And so that's something to keep in mind. We looked at tally, we looked at the one method. Those are pretty cool. Also, like when you're going through finding paths, it can be helpful to just work directly with the paths themselves sometimes, rather than just like indexes or kind of like references. So yeah, I don't know. Hopefully that's helpful. Thanks so much for watching, and we'll see you in the next one.